Hello students, so we are starting chapter 2, and chapter 2 is the basics of organic chemistry, just setting down the foundation. So some of this is going to be review for you, but then there's also a lot of new stuff. The first thing I'm going to cover is just polarity, just because that's really important for understanding reactivity, where certain molecules are going to attack on a molecule, and then formal charge is an important part of that, and looking at curved arrow notation, which I suspect is new. So polarity is based on electronegativity. When you have a bond, if you have a decent difference in electronegativity, you're going to have polarity there, a polar bond. So this is Linus Pauling's electronegativity scale. Fluorine is the most polar in the upper right, and the least polar is down at cesium in the lower left. Electronegativity is the tendency for an atom to attract electrons. So that's going to be due to the number of protons it has and its size. When you bond atoms, then you have this electron tug of war between atoms because there are electrons between them. So the electrons may not sit perfectly in between them. When you have two atoms that are identical, for example, chlorine and chlorine, then yeah, there is no pull or tug on the electrons. So you have a nonpolar covalent bond that is equally shared. However, if you have something like hydrogen and chlorine, H over here, and Cl on the right in the halogen group, then you are going to have a difference in electronegativity. You don't need to know or memorize these numbers, but you could get a feel for it just by where atoms are on the periodic table. That's going to lead to a polar covalent bond. Anything more dramatic, metals and nonmetals, usually give rise to ionic bonds. You'll need to get a sense for whether molecules have a dipole moment. So there's also a net dipole for a whole molecule. A dipole is shown using an arrow towards the more electronegative atom, and that's the partial negative end given delta negative, and then the barbed end or plus end of the arrow is towards the more partial positive, H in this example. So there's a real magnitude and direction to these dipoles, and overall in a molecule you would kind of make those additive. What's cool is in your book, they really do a nice job of throughout the whole semester showing these electrostatic potential maps, which are basically color maps. You guys will be able to draw your own maps of molecules in one of your modeling labs. But right now, just looking at the pictures, what this tells us is where the electron density is. The more red the area, the more electron density there is. The more blue, the less. So red is more partial negative, electron rich region. Blue is more partial positive. So we can see that with HF. H is on the left here, and it's more partial positive, and that's because fluorine is more electronegative. So it's going to pull more electron density. It'll be the more red end. This is useful because it can help you understand what parts of the molecule are positive and negative, and that can explain a lot of things: acidity, basicity, how different molecules are going to react. If there is no difference in electronegativity, like in the hydrogen molecule, it's all green and nonpolar. In something more of more ionic, on the ionic end, like sodium chloride, you'll see a more pronounced difference in the mapping. So I mentioned molecules can have an overall net dipole moment. So that's going to depend both on whether or not there's bond polarity and will depend on the geometry. Because if a molecule is perfectly symmetric, then bond dipoles can cancel out. So let me give you an example. Here is ammonia. Because of the lone pair, it's trigonal pyramidal, and the lone pair, electrons in the lone pair have negative charge. So there is, you could think of a dipole towards the lone pair. Overall, there are also these individual and H dipoles. Overall, the net dipole is going up, and there is a certain number you can associate with that. It's mu, or the dipole moment, and it's 1.47 dBi for ammonia. You can calculate that. We're not going to do that in this course. I just wanted to show you that's out there. Water's 1.85. So this could give you a feel for the magnitudes of the dipole moments. We actually don't look at those, but I want to show you here for tetrachloromethane, you have bond dipoles between the C and Cl going towards the more electronegative chlorine, but this molecule is perfectly symmetric as a tetrahedral molecule. So all those dipoles have an equal pole. Just think of four identical quadruplets pulling on a rope. It's not going to go anywhere. No one's going to pull stronger than the other. So the overall net dipole moment is 0, and that molecule is nonpolar. So this is real. This is perfectly symmetric, nonpolar. This is going to be polar. That they're going to have very, very different behavior. Formal charge is very important. So this is an area when you're drawing electron dot structures, later on resonance structures, you need to be able to capture formal charge, which is basically when a molecule does not have its normal bonding. For example, in this glycine molecule below, oxygen typically likes 2 bonds and 2 lone pairs. This oxygen has 1 bond and 3 lone pairs. So I know it's not the normal bonding. It's not going to have a 0 formal charge like this upper one. It's going to have a negative formal charge. How do you know the number? You can use this formula. The group number off the periodic table for oxygen is 6. This is what it should have, minus what it actually has. So minus the number of non-bonding electrons, so the electrons, count the individual electrons in the lone pairs, minus half of the shared electrons, which is essentially minus the number of bonds it has. So let's look at this top one here. Oxygen's in group 6, minus 1, 2, 3, 4 lone pair electrons, or 4 non-bonding, minus 2 bonds, 0 formal charge. This lower one, though, it has 6, but it's sharing more than that. So that means it's going to have an extra electron share, so it'll have a -1, but you could calculate it here. Group 6 minus 1, 2, 3, 4, 5, 6 non-bonding electrons, minus 1 bond, that gives a -1 charge. So you could think of the half a shared electrons as the same thing as the number of bonds. Let's do the N over here. I moved to the N because the carbons have the normal 4 bonds like it usually has. Nitrogen likes to have 3 bonds in a lone pair. This has 4 bonds, so it's in group 5, so 5 minus 0, because it doesn't have any lone pairs, minus 4 bonds equals +1. Notice that all the formal charges add up to the overall charge of the molecule. The overall molecule is neutral, so the overall added charges for formal charges is 0. This is a slide to show you just the most important ones, the most common ones you see. Usually, carbon, nitrogen, and oxygen have this bonding, and the formal charge is 0. However, as we saw in the previous slide, if oxygen, instead of one of its bonds becomes a lone pair, it has a minus charge. If nitrogen shares its lone pair as a bond, it ends up with a plus charge. The other ones that are common are oxygen with 3 bonds in a lone pair. You'll calculate that. You'll see that all the time. Just get used to that. When you see oxygen with 3 bonds in a lone pair, +1 charge. This is the most important one you'll use in this whole course. And it gets a special name. It's a carbocation. If carbon doesn't have one of its bonds, it means it no longer has its full octet of 8. It only has 6 electrons around it, 2, 4, 6. And so it gets a +1 formal charge. It's carbon with 3 bonds and 0 lone pairs. So it's a group 4 minus 3 bonds, it gets a +1 charge. If there are formal charges on an atom, you have to indicate that. That's important because of the way we draw structures, we need to indicate formal charges to note any deviation from bonding. So make sure you do that on any quizzes or exams. And actually, we won't have quizzes, but on exams and any worksheets. Okay. The last topic we'll cover are using curved arrow notation. So there's a difference in types of arrows you use. This is the most important notation you'll use in showing how molecules react. They're used to show the movement of electrons. This is critical because 2 electrons equal a bond. So you're basically showing how bonds form, how bonds break. The arrow tail starts at the electrons that are moving, and the arrow head shows where it's moving to. A fishhook arrow, this is a little different. So this is a double-headed arrow. This one only has 1 fishhook arrow end, and that represents moving 1 single electron. You will use this because it's used for radical reactions, and we'll talk about that more later. Let's do an example. Let's just get into your first organic reaction here. We have ammonia plus borane, BH3. What are you going to get out of it? First of all, I'm going to introduce 2 terms to you, nucleophilic and electrophilic. Nitrogen is nucleophilic. It's nuclei loving. It has a lone pair and it's seeking out something positive, a positive nucleus. So a nucleophile, which nitrogen is here, this molecule, ammonia, the nitrogen in that is an electron-rich atom. Sometimes nucleophiles can be negatively charged, and it has a free lone pair, which it can donate to another atom. The opposite of that would be an electrophile. So the boron atom is electrophilic. It's electron loving. And so the main reason why that is boron has 6 electrons. It's okay with 6, but it could do with 2 more. So it's an electron poor atom. It has some vacant orbitals that it can allow electrons to come in. And so it wants to accept electrons from a nucleophile. So if you get these 2 guys together, boron saying, hey, I want 2 more, nitrogen saying, hey, I've got 2. So use the curved arrow notation, those 2 electrons will go to form a bond to boron. Because boron has 6 and can accept 8 total, that's all that needs to happen. You form a nitrogen boron bond, and then notice, because nitrogen's sharing this lone pair now, it gets the plus formal charge, and boron has 2 more electrons than it normally would, it has a minus formal charge. Let's look at something similar, but where you don't have something like boron with an open vacant orbital and only 6 electrons, but something that already has a full octet. So if something already has a full octet and a nucleophile wants to come in and attack it, something has to give. A bond has to break or move somewhere else. So I'm going to show that example. I have NH2 minus. So now this nitrogen doesn't have an H. Instead, it has 2 lone pairs, and it gets a -1 formal charge. It's going to react with formaldehyde. So you could draw this structure with a CC double bond, a CO double bond. And when you get these 2 together, you know that the N is nucleophilic. It's got this negative charge. It's got 2 lone pairs, actually. And so your electrophile is this other guy. I know it's an electrophile because if I look at the structure, I know it has a resonance structure. I can show it down here, where you could take the pi bond here, those electrons, and put it up on the lone pair as a lone pair. And you see that this carbon is partial positive. So in this case, it has a positive formal charge, but overall in the molecule, it's a partial positive charge. So plus attracts minus, the minus charge of the N and its lone pair will go to this carbon. And because carbon cannot have 5 bonds, this pi bond has to break, and the 2 electrons in this pi bond go up onto this O. This is a very classic reaction. Some sort of nucleophile attacking the CO double bond, we call that a carbonyl. Notice that the lone pair forms a bond, then the bond becomes a lone pair, formal charges change, nitrogen is now neutral, and then the O has an extra lone pair up here, it gets a minus charge. Again, the resonance form explains the reactivity at the carbon center. Even though this resonance form is minor, it shows that there's a negative character to the O, but more importantly for us in this reaction, a positive character to the C. So that you could draw a dipole for the CO bond showing partial positive. Okay, that's going to end this video, and I will continue next time more with resonance structures.